Okay, great. Okay, we are at critical mass with about 2/3 of the audience here. So we will get started. Welcome to the spring semester. Welcome to the spring colloquium. And I'm happy to introduce our first speaker, Victor Zhong. Victor is a PhD student at the University of Washington. He's working with Luc Zettelmoyer, and he is also a visiting researcher at Facebook, AI Research. And his work is supported by an Apple scholarship in AI and machine learning. Previously, before his PhD program, he got his master's degree in the Stanford NLP group and has also worked at Salesforce. We're very happy to welcome him today, and he will be talking about reading to generalize. So Victor, please go ahead.
All right, thank you, Lori, for the introduction. Good afternoon, everyone. Thank you for inviting me. I'm super excited to be here today to share with you our work on reading to generalize. So this presentation is about, I think, 50 minutes. It's in 3 parts, so I'll try to take some questions after each part, and then, as usual, we'll take questions at the end as well. All right, let's get started. So the motivation for this work is that machine learning models typically train on very large fixed data sets, and they do not generalize to even closely related problems. So for example, an object recognition system requires millions of annotated images, and then it cannot classify new object types after deployment. For example, you're training an ImageNet and then you deploy it to do item or product classification in a grocery store. A dialogue system requires difficult to annotate conversations, and they cannot converse about new topics that emerge. For example, if you're training on restaurant reservation or something about restaurants, and then you want to deploy this dialogue system, and someone comes to you and asks you about whether they need to pay income tax. And a robot trained to navigate one space learns policies that do not work in new spaces. For example, you train on academic data sets on houses, but then you're deploying to a warehouse. So for many such problems, large-scale data gathering is difficult, but the collection of specifications, text specifications, high-level language descriptions of what the problem is and how the algorithm should behave is relatively easy. So for example, in object recognition, oh, actually, let's talk about the examples later. But the question that we want to ask here is as follows. By reading language specifications that characterize key aspects of the problem, can we learn solutions that generalize to new problems? So what would this look like? So for the previous examples, the object recognition systems identifies new products by reading about product descriptions. So for example, you can show the model descriptions of class types during training for these different animals. And then during inference, you can show it descriptions of particular products like milk cartons. The dialogue system converses about new topics by reading descriptions of these new topics. For example, whether someone needs to pay tax or how restaurants are structured or what kind of restaurants there are. And similarly, the robot identifies appropriate policies in the new space by reading about the items and the layout that's present in the new space. So prior work in machine reading focused on things like question answering and task-oriented dialogue. So for example, in question answering, our models read to solve a fixed task, for example, to find the question's answer. Similarly, in task-oriented dialogue system, we read user utterances to help the user achieve a fixed goal. For example, to book a restaurant and so forth. So in contrast here, we're examining this notion of reading specifications, not as an end, but as a means to generalize new problems. So first, we'll look at generalizing to new domains by reading domain text using task-oriented dialogue as a case study. Next, we'll look at how to read to generalize in the event that there is no naturally occurring domain text. And here we'll look at zero-shot semantic parsing as an example. In particular, we'll look at text-to-SQL parsing, where the parser generalizes by reading structures in the database schema. And third, we'll look at a more challenging case where no supervised training data is available, from which we can learn how to ground the text that we're reading to the end task. The case study that we'll look at here is policy learning for new environments by reading high-level rules of the environment in the form of text manuals. And I'll conclude with a discussion of open challenges in generalization via reading. Ultimately, through reading, what we want to do is to make machine learning accessible in low resource domains where the practitioner cannot obtain large quantities of annotated data. So let's start with the most intuitive approach, which is a generalization to new domains by reading domain text. And we'll look at this through the example of task-oriented dialogue. So a standard approach for task-oriented dialogue is to decouple the problem into three subproblems. They are state tracking, which maps user utterances to a set of slot value pairs from an ontology. Policy, which decides the action the agent should take given the state that we're in response to the user. And response generation, where the action and its results, for example, a database query and the subsequent rows that are retrieved, are used to generate a language response to the user. A key limitation of this approach is that it assumes an ontology to map to. This means that we must collect data with respect to an ontology, and the dialogue agent, which is trained using this ontology-specific data, does not generalize to new domains with new ontologies. So for example, on the right, we see a simple ontology from the restaurant reservation domain. So you would have things like a price range for the restaurant, location of the restaurant, its phone number, cuisine types. These are slots. And the values here, for example, for cuisine would be things like the types of food, like Chinese food, French food, Japanese food, so forth. So the question is, how do we build task-oriented dialogue systems that generalize to new domains? For example, if we train on many things, including restaurants, but then during evaluation, the user comes and talks to us about paying taxes on pensions. So one approach here is called conversational machine reading. Short form is CMR. It's proposed by Sebastian Riedel's group at UCL. And it conditions a dialogue agent on domain-specific documents. So in CMR, the agent helps users answer high-level questions by participating in an information gathering dialogue. So here's an example of CMR. So initially, the user comes and, so suppose we're a dialogue agent, the user comes and provides some initial context. So here the user says, I get my money from a business I have. We get our funding from a private bank. Next, the user specifies their information need via question. And in this case, they ask, do I need to pay tax on my pension? The agent then references a document to identify what information is missing in order to answer that question. So this particular document that we're looking at has to do with paying taxes when you live abroad. And it says, if you're not a UK resident, you don't usually pay UK tax on your pension. Super exciting document, by the way. But you might have to pay tax in the country you live in. There are a few exceptions. For example, UK civil service pensions will always be taxed in the UK. So in this case, we see that the user needs to pay tax if they are resident or if they receive UK civil service pensions. So now the user the agent converses with the user to fill in the information in order to resolve the information need. So in this case, in a previous turn, the model asked the user, are you a UK resident? To which the user answered no. So then in this turn, the model proceeds to ask if they receive UK civil service pensions. The ultimate outcome of this dialogue is that the model answers with a yes, a no, or I don't know. So this is a kind of a limiting constraint of this particular task, but this is how the dialogue get resolved here. And during evaluation, the agent must answer information requests on new topics that it hasn't seen before that comes with new documents. So this tests for generalization to new domains. So how do we model this decision-making process? So we developed a model for CMR, which instead of generating the response word by word, as is fairly common in a lot of open-ended dialogue problems, we retrieve and edit the relevant content from the domain documents and dialogue history. The key observation here is that responses in task-oriented dialogue usually consist of domain-specific content and general question answering syntax. The latter is easy to learn because it is shared across domains. The former is domain specific, and therefore we employ an extract and edit technique to allow the model to generate precise references in new domains. So the name of this method is entailment-driven extracting and editing, or E3, which describes the stages of the model. So I'm going to talk about a number of models in this work, but I won't go into the specific architecture in detail due to time consideration, but I'll go over them at a high level. So let's talk about this particular model and what it does. So given the domain document and the conversation context, and here I've just copied over the example that we were looking at before about who needs to pay taxes on UK taxes on the pension. So what we're going to do is first we'll extract the rules or the clauses that are relevant to the information need. So in this case, we need to determine whether the user is a UK resident and whether they receive UK civil service pensions. And next, we'll compute a score to track which of these clauses have been addressed already. So in this case, we previously asked the user whether they are a UK resident, to which they replied no. So we consider this particular clause to be talked about. And finally, we decide on how to respond. So for this particular task, we can respond by answering yes, no, I don't know, and these conclude the dialogue. Or we can continue the dialogue by asking a follow-up question. So in this case, we ask the user a follow-up question by inquiring about this remaining clause, which is UK civil service pensions. And this results in the question, are you receiving UK civil service pensions? And this response at the bottom is formulated by editing the extracted clause we want to inquire about with a sequence-to-sequence editor. So we evaluate E3 on new dialogues from the Shark CMR task. We compare E3 to a sequence-to-sequence BERT model, a hand-engineered dialogue system designed specifically for this task, as well as a extractive BERT QA model. So these are the models that you typically see on things like Squad and so forth. We evaluate on decision accuracy, which is how often the model's decisions to answer yes, no, I don't know, or inquire match the decisions that are made by humans on a turn basis. We also evaluate the inquiry relevance through blue scores. And this is when the model decides to ask a follow-up question, how relevant is the question compared to human written questions? And we see here that this model, E3, outperforms previous methods in terms of the decision accuracy and the inquiry relevancy. We also ablate E3 by progressively removing its components. So for example, we can remove the final editing components. We remove the stages that corresponds to entailment and also extracting clauses, at which point this model is basically the same as a extractive QA model. So we find that extracting implicit rules from the text, reasoning over the entailment, and editing the inquiries improve both decision accuracy and inquiry relevance. So all of the components, or all the E's in E3, are complementary. So here are some examples from E3. This is from the evaluation set. So we have a document regarding how to quantify for additional state pension. So it says something like, you get additional state pension automatically if you're eligible for it, unless you've contracted out of it. The initial user scenario is, at no time were my contributions lower than anyone else's in the SERP. were ever paid into a private pension. And the question is, do I get additional state pensions automatically? So the underlying spans in this case indicate the extracted clauses by the model. The three scores respectively correspond to the inquiry score, which is if the model asks the question, what's its preference in terms of which clause does it want to inquire about? The second score in red is the entailment score from the previous interactions. And the last one is the entailment score from the initial context. So these are the degrees to which the model believes the particular clause has been talked about in these contexts. So in this case, the model thinks both the clauses have been discussed in previous interactions. In particular, we previously asked the user, are you eligible? They answered yes. And then we asked, have you contracted out of it? And the user also answered yes. So the model finally assigns a high confidence to answering no, which is the correct answer. Here's another example. So in this case, well, I'll just read this real quick. It's not super long. It says, if you're a female Vietnam veteran with a child who has a birth defect, or you are a child of a female Vietnam veteran with a birth defect, the child may be eligible for VA finance care. This scenario, I make $14,000. I would like to keep making that until I return to Zimbabwe. And the question is my child eligible for VA finance healthcare? So here, none of the clauses have been discussed. We have no previous interactions with the user. So the model assigns a high probability to inquiry, and you can see this by reading off the decision score. So then we inquire about the first clause, which is a female Vietnam veteran with a child who has a birth defect. And we're going to edit this to obtain the follow-up question, are you a female Vietnam veteran with a child who has a birth defect? So compared to word-level sequence models, E3 has the additional benefit of being interpretable as well as having good performance because we can essentially peek into its decision-making process. Are there any questions about this work so far? It can take like 2 minutes or something. Someone has his hand up.
Yeah, hi.
Hi.
I have a question. Like if the decision is inquire, then how does the model decide what query to, like, what should be the follow-up question?
Yeah, so we actually train this model end to end. So let me see if I can, oh, here it is. So we have a entailment module that kind of computes scores, which is the extent to which we believe a particular clause is extracted. And these scores are used as features later on. So the model is trained to maximize likelihood of the correct answer. So we don't really have a handcrafted decision-making process as to, here are the clauses that we talked about. What do you want to talk about next? Does that answer your question?
Yeah, thanks.
Cool.
No other questions? Oh, Sri, you still have your hand up. Is that for something else? Okay. I don't see any other questions, so I guess you can go on.
Sounds good. So in summary, in this section, we examined generalizing task-oriented dialogue systems to new domains by reading domain text. We made the observation that response generation can sometimes be decoupled into precise content and general syntax, and that we can generalize to new domains by extracting content and editing them to fluent responses. But this makes the assumption that we have naturally occurring domain text. So what happens if we do not have naturally occurring domain text? So let's look at such a problem in semantic parsing on new databases, where instead of having access to text descriptions of what the database is about, we only have an outline of its symbolic structure in the form of a database schema. So there are many applications for semantic parsing. Today, we're going to talk about a specific application of language to SQL parsing. So in traditional language to SQL parsing, we're given an underlying database, and our task is to translate natural language queries into SQL queries on the database. So for example, we have a question that says, which airports are in Seattle, Washington? We have a database about many things like airports, flights, and etc. And we want to obtain the SQL query select name from airports where location equals Seattle. So like how traditional dialogue systems assume an ontology, traditional parsers assume a database and do not generalize to new databases. So we make an implicit assumption that the deployment database is identical to that used during training. And this is a strong assumption, definitely. The question is, how can we generalize to new databases? So for example, if we're training on different databases like things about flights, things about restaurants, can we deploy to something else like a sports database, for example? And this is common, for example, if you're, oh, we have a question from Jeremiah. Please go ahead.
Yeah, I was just wondering if you could give us a little bit on how you characterize different databases, whether you're looking at different domains or databases that say have different fields for the entries in the database.
Yeah, so I'm talking about cases where you're essentially migrating to an entirely new database. So you can think about this in the case where, for example, you're at a company and then you say, I want to train a semantic parser. So you build a prototype and you're training on things like the ADIS database, for example, or Spider or something like that. It consists of things like students, schools, whatever. And each time, so in the traditional case, you would just, take the queries and annotations on that database, and then you would try to deploy it. But then you might be deploying it to new things like sales figures for the company. So the semantic parser wouldn't work because it's assuming that we're still talking about students and schools. So it would break down. So in this case, I'm showing an example where we're training on database of flights. So you're talking about things like airports and flights and so forth. But then we want to deploy it to something about sports, which talks about teams and matches. So usually this wouldn't work. So I'll talk about next how to make this work. Does that make sense?
Yeah, I guess I'm kind of wondering for this, generalization question. In the first example database here, you have questions like which airports are in Seattle, Washington.
Yeah.
You could imagine that this would generalize well, or under some circumstances would generalize to a database that had, that is being used to answer questions like which restaurants are in New York. As long as you sort of have the database itself structured in the same way,
yes,
where the airports exist in the same,
or
column, just like restaurants.
And that's kind of how
కొత్త type of language వస్తుంది కదా sports గురించి కూడా.
I'm sorry, could you repeat that? Okay, never mind. Yes, so we'll talk about how this ends up being used, and you're exactly right. So what happens is that we have models instead. So usually in this case, the model just looks at the natural language utterance, and once it's trained on sufficient quantity of these, it can generalize to new queries on the same database. And then we have models that also look at the database schema, and these models will to some extent generalize to new databases. This is, I think, what you're talking about.
Yeah, okay, cool, thanks.
So again, we want to answer the question of how we can generalize to new databases. So in recent years, we started to look at problems where the parser indeed must generalize new databases. So like how CMR generalizes to new domains by reading domain text, here the parser generalizes to new databases by reading database schema. So in this particular case, we have a table called CFL draft. It has things like the pick number in which a player is drafted, the team that drafted the player, the name of the player, the position that the player played, and the college that this person attended. So in this case, So previously, what the model would receive is it would just see how many teams drafted from your college. In this case, what the model receives as input is not just the question, how many teams drafted from your college, but also the schema of the table CFL draft. So it sees the columns pick number, CFL team, player, position, college, and so forth. And unlike the previous problem of conversational dialogue, there are no domain documents written to help us understand the problem. And instead, we have a user-constrained database of facts, most of which are irrelevant to the query at hand. So a core challenge here is to ground the reference in language to elements such as columns in the database schema. So here, for example, we want to know that the word teams corresponds to the column CFL team. What's implied here is that drafted from means the college that you're drafted from and so forth. So how do these parsers work? So typically what happens is that we start off with the database schema and the user utterance. And by the way, I believe the new models still kind of look like this. They are to some extent simplified because now we have language models and we know how to kind of look at longer and longer context. But in essence, this is still kind of what these models look like today. So our database has a bunch of tables, each of which has its own schema. So what we're going to do is for each table, we'll concatenate its schema with the utterance to form a set of input sequences. So these will look like, for example, for the students table, we'll have the utterance, how many students attended Highland Secondary, concatenated with the schema of the table that's serialized. For example, the name of the table students, we have a key that's called ID, we have a key that's called school, and so forth. So we're going to encode each of these sequences with a pre-trained transformer like BERT. For each of these tables, we're going to, again, each of the tables are serialized. We're going to extract spans from its table representation to build candidate phrase representations. And each phrase here will correspond to things like table names, column names, and so forth. And then we'll select between these phrases and a fixed set of syntax keywords to formulate a SQL template. So these are essentially SQL queries without values. So we'll have things like select count students where school equals to placeholder. And finally, we'll fill in these templates by selecting words from the user utterance. And so, for example, we'll fill in the placeholder previously with the phrase Highland Secondary. So we use this parser for 3 language to SQL tasks. These range from Spider, the type of parsing problems I showed you earlier, but with multiple tables. So these will be things like, so this is a top figure, and this is, we have a database that we observe. We also have the utterance for each stadium, how many concerts are there, and our job is to produce the logical form, which is this particular SQL that you see here. We also do things on tasks like CoSQL and Spark, which are conversational parsing, where utterances, in addition to referring to things from the database, it can refer to things from previous terms. So the example here being, we receive the database as input. We also see the previous utterances, how many dorms have a TV lounge, and the logical form that we produce. And this turn, the user asks, is the total capacity of, what is the total capacity of these dorms? And the phrase these dorms here refer to dorms that have a TV lounge. Sorry, is there another question, or is the, oh, no, okay. So again, in evaluation.
Oh, sorry,
oh,
Victor. I think Rich has a question.
Yes, go ahead.
Hi, sorry, I raised my hand right after you asked. But I'm wondering about your evaluation accuracy in these cases, because I can see three kind of possible options here. One is a kind of like direct text to text to the SQL. One is doing some sort of like normalization on the SQL to say like, okay, you might express something a little bit differently, but this is functionally identical.
Yeah.
But then there's also a third thing of like, do you pull back the correct rows no matter what kind of SQL you've written? What are you doing here? And
yeah, that's a great question. So I'm only showing the execution accuracy here. So execution accuracy is basically you retrieve the correct rows. When the paper, we also evaluate, and this is part of the blind test, on logical form accuracy, which is essentially similar to kind of matching surface forms, but with some editing to make sure that the equivalent queries are considered. So this is kind of like more looking at just your SQL query itself and seeing whether that matches what the humans annotated. You can also do execution accuracy, and someone else from Berkeley also proposed a kind of a almost adversarial evaluation where you're kind of evaluating for different perturbed utterances and seeing whether your SQL execution is correct. So those are kind of the evaluations that you see for these tasks typically. Does that answer your question?
Yep, thank you.
Cool. So in evaluation here, we evaluate on new databases and queries on those new databases. So we find that this parser does indeed generalize new databases by reading schema. So on the right here, we're seeing the execution accuracy on Spider, Spark, and CoSQL. We typically see a performance degradation once we go to multi-term parsing because references to previous terms is more difficult to interpret. So we have this parser, but that looks like the database schema in order to generalize, but the fundamental setup of traditional parsing remains, which is we train a parser, we throw it into the wild, and we hope that it is able to read new database schemas. So if you've ever read new database schema, you kind of know they're much more difficult to transfer between the natural language domain text because they contain new symbolic structures. So how can we adapt the parser better? So in 2020, we had another idea of how to improve this use of schema reading, and that is to synthesize adaptation data so that the model can familiarize itself with the language and the structures of the new database. So we call this technique GASP for grounded adaptation. So we start off as before by training a semantic parser on the training data to produce SQL. And here the light blue box is the training environment, or in this case, a database. And the purple one is the inference database. So as before, we train a semantic parser on the training data to produce SQL. Next, in the reverse direction, we train a utterance generator. So this is using the training data, but instead of producing SQL from language, we're going to produce language from SQL. So once we have these two models, we go into the new database and we start to sample logical forms with respect to a SQL grammar. And this is relatively straightforward because we know how SQL grammar is. It's not terribly complicated. And once we have access to the content and the schema of the new database, we can essentially synthesize queries here. And we give these samples to the utterance generator to obtain synthesized utterances in this new database. So now we have sampled SQL on the new database as well as synthesized utterances. So then now we parse the synthesized utterances using our previously trained parser to obtain synthesized SQL for the new database. So now we essentially have augmentation data or adaptation data on the new database. But this process is very noisy because as you saw from before, the models have something like 60% execution accuracy. So they're not terribly great when they're doing this generalization to begin with. So this process is very noisy. And therefore, we verify consistency in the form of execution consistency and logical form consistency between the synthesized SQL and utterance pair and the initially sampled SQL. So if these two match, we have some idea that this synthesis cycle is correct. So once we have these consistent examples, we're going to use them to adapt the parser to the new database. So using this technique, again, we're looking at the 3 previous data sets. We see improvements across all 3 tasks when we compare GASP to the baseline parser that we are adapting. We also perform some ablations. So one very intuitive thing to compare to is data augmentation. So the distinction here is that adaptation is synthesizing data on the new database, whereas augmentation is synthesizing data on the training database. So we find that adaptation on the new database outperforms data augmentation on the training database. This is shown by comparing the green to the blue. So for this experiment, we synthesize the same quantity of data on the training database instead of on the inference database. And we also perform consistency checking here. We find that retraining the model on this data leads to overfitting. Another thing that we note is that cycle consistency checking is very important to obtain these adaptation gains. This is shown in red. So for this experiment, we don't check for consistency, and instead we keep all the synthesized queries. And this results in twice as much data, but most of these are inconsistent. And when we include this inconsistent data, it degrades performance. So by combining synthesis with consistency checking on the new database, GASP is able to improve the baseline parser. Are there any questions about what we talked about so far? Cool. So far, we've looked at generalization to new domains by reading domain text. Then we looked at generalization by reading in cases where no domain text is available. Namely, we looked at generalization to new databases and semantic parsing, where the parser reads the database schema or synthesizes data on the new database using the database schema. So both of these works assume that there is a large quantity of supervised data for training, from which we can essentially learn how to ground the text that we're reading or the structure that we're reading to the end task. So in the first case, the supervised data taught us how to ground domain text to task-oriented dialogue. In the second case, the supervised data taught us how to ground database schema to semantic parsing. So what if we do not have access to supervised data from which we can learn how to read? So let's look at this case through the example of policy learning on new environments. And what we'll do here is we'll read the environment manual for the new environment. So in traditional policy learning, we have an agent that interacts with the environment to accomplish some objective. When it makes progress towards accomplishing the objective, the agent is rewarded. Because the agent only observes delayed sparse rewards and does not obtain step-by-step guidance on how to behave as it would in supervised or imitation learning. For example, in the dialogue case, we had annotations for each turn on how the agent's supposed to behave. Similarly, in turn-by-turn semantic parsing, for each turn, we have the correct logical form. So policy learning is very noisy and expensive because it doesn't have that step-by-step guidance. And what it only has is the delayed reward in a lot of cases at the very end. So it's not uncommon for a policy learner to require millions and even billions of steps on reasonably complicated environments, such as NetHack or robotic grasping and so forth. After training such an expensive policy, the problem is we find that it doesn't generalize to even slightly different environments. So for example, you train a gripper to grasp objects, and if the gripper traction of the robot arm is stronger or weaker, this doesn't work. If you train a agent to play games and the end game boss attacks faster, your policy breaks. And if the map layout that we're navigating, if you train a navigation agent, if the layout changes, the agent breaks again, and so forth. So this is clearly suboptimal. Ideally, after putting in so much time and compute into training this agent, we would like it to generalize to new environments. And following the previous work, the question is whether we can generalize policy learning via reading manuals about the new environments. So this is a kind of a proof of concept idea. Initially, we weren't sure whether this would work at all. So to evaluate this idea, we designed a new environment specifically to test for generalization. And this is typically not done in reinforcement learning. In reinforcement learning, you typically evaluate either on the same environment or on just very slightly different environment. So this is how our evaluation works. So we design a procedurally generated suite of games with a combinatorially large set of dynamics, as in high-level rules of how the game works, and the accompanying text descriptions. And this is what each game looks like. So for each game, we have a manual that specifies high-level game rules, as well as a goal for this particular game instance. So with this manual and goal in mind, the agent is then placed into a world. So let's look at this particular game instance. We obtain a document and it says, the Rebel Enclave consists of Jackal, Spider, and Warg. Arcane blessed items are used for poison monsters. Star Lions contains Bat, Panther, and Wolf. Goblin, Jaguar, and Lynx are on the same team. They are in the order of the forest. Gleaming and mysterious weapons beat cold monsters. Lightning monsters are weak against grandmasters and soldiers' weapons. Fire monsters are defeated by fanatical and shimmering weapons. And the goal here is to defeat the order of the forest. So this manual is not specific to this particular game world. So only a subset of its content are relevant. This is similar to the case for semantic parsing, where we have a database, but not all of its content is relevant to the particular query that we're seeing. So in this case, to figure out the correct strategy, first we identify that the goblin is on the target team, which is the order of the forest, by reading the manual. Next, we look at the game world and we find that the goblin in this specific game is a fire goblin. So then referring back to the manual, we know that we must find a fanatical or shimmering weapon. And we look back to the game world and we see that there is a fanatical sword. So the first step then is to flee the monsters until we acquire the fanatical sword. And once we have the sword, we flee from the bat, which is not the target monster, and we engage the goblin, which is the target monster. And finally, we win by beating the goblin. And note that if we do not follow this precise reasoning procedure, the agent loses. Moreover, we can only determine the correct course of action by grounding the game to the manual. So we designed this in mind, with this in mind, so that the agent can't really win the game without understanding what's in the text. And finally, we cannot internalize any particular game because the evaluation is on a held out set of games and dynamics and manuals. So the key challenge in this setting is the ability to cross-reference text manual and world observations. In order to do this, we proposed a policy learner we call text-to-pi. It relies on a new bidirectional feature-wise linear modulation layer, which basically jointly encodes the manual and world observations. You can look at this kind of as a convolution layer that has two modalities of input, and it also has these cross attentions in itself to combine these inputs. So we're going to stack these layers similar to how you would stack convolutions to model this multi-step reference procedure that I showed you earlier. And again, in the interest of time, I won't dive into too much modeling details about this particular architecture. So with this model, we see that we are able to zero-shot our policy to new games. So first, we see that this method, which are the bars on the far right, outperforms previous language grounding models. These include these LSTM convolution models on the far left. And in the middle, we have the film models by Ethan Perez. Second, we see that this result is consistent when generalizing to games with different grid sizes. So the blue bars here, we're showing, this is typically how the blue bars are what you would see in reinforcement learning work typically. These are the asymptotic performance on your training distribution of environments. And the orange ones here are, so we train on 6x6 worlds, and the orange ones are also we take essentially the 6x6 world trained policies, and we evaluated them on new 6x6 worlds. So this is train 6x6, evaluate on new 6x6. And the green bars are train 6x6 and evaluate on new 10x10. So this suggests that the reading policy learner has learned strategies that generalize beyond its training world distribution. We're also able to create a curriculum to train this agent to progressively more games. Alex, you have a question?
Yeah, it was on the last slide.
Mm-hmm.
So sorry, as I understood the argument, or maybe it was that one. As I understood the argument was that this was intended to generalize better to new environments, but then wouldn't the measure of that be the difference between train and the two test environments? And it seems like while TextApply does much better on the overall accuracy, the other like film, for example, does just about as well on train and test 6x6 and test. And the difference between that and test 10x10 seems similar to your model. Did I understand that correctly?
I think that's a good point. So you're saying maybe we should be measuring the delta instead, is that correct?
Yeah, like, or I guess only if the generalization performance is like the stated novelty, because it seems like you're definitely doing much better on the task. So that's definitely like a novelty, but it also seemed like you were saying that the generalization was better. And so in that case, the delta would be more important, right?
Yeah, I think that's a reasonable way to think about it. I think generalization, so in this case, it's slightly tricky because what we're training on is not a single environment, but a very large set of procedurally generated environments. So what we see with the other models is that they're basically underfitting because they can't learn enough things to even accommodate new environments in the training distribution. So we see lower training performance, and we also see that when we carry that over to the test environments, we see lower test performance as well. But yeah, I think you raise a reasonable point. I don't think there's a clear consensus on when we talk about generalization, do we mean like good performance on held out test sets, or do we mean like the gap between training and test?
Right. But it seems like you made a good point too, which is if the train environment, the test environment are procedurally generated, there's generalization baked into each of those categories because of the variance in them.
Yes.
Okay, that makes sense. Thank you.
Cool. So we create a curriculum to train this agent to progressively more difficult games. By the way, this environment this suite is called RTFM, which in the paper it stands for Reading to Fight Monsters. So the figure on the right here shows the performance on the most difficult games after training on each stage of the curriculum. So initially we see that if we train on simpler games, first of all, if we train on difficult games, it doesn't learn. If we train on simpler games, when we evaluate on hard games, the performance is poor. But if we gradually step up in the curriculum, we obtain better and better performance. And the difficulty here stem from things like moving monsters that chase the agent, multiple distractor entities in the game, and the manual, as well as randomized language templates written by humans. Again, you only receive a reward at the end. So these kind of stochastic movements and different failure cases will make the learning process more complicated, as well as it makes the grounding more complicated with the distractor entities. So once we do curriculum training, we find that the policies obtained from curriculum training also generalize to new games and new world sizes. So here we're showing things like training on 6x6, evaluating 6x6. training 6x6, evaluating 10x10, and training 10x10 and evaluating 10x10. Then we know that 10x10 is just more difficult to learn from as well. So our RTFM results show that, yes, we can indeed generalize new environments without supervised data to tell us how to read. Our subsequent work in this area have shown further evidence for reading to generalize. Our recent ICML work on Messenger showed similar generalization results in a more challenging setting where the agent must also learn to map discrete entity symbols to natural language references in the manual. So in RTFM, the references in the manual and in the world grid are both language. Here, the world grid references are discrete symbolic IDs. So therefore, we must learn that additional grounding step between those IDs and the manual without relying on things like word overlap and so forth, or compositionality. So in our latest NeurIPS effort, we put in a lot of work and we combined a number of language grounding environments. So in addition to RTFM and Messenger, we also have NetHack, which is a popular and notoriously difficult roguelike game. We have AlfWorld, which is a text-based kitchen navigation object manipulation environment, and Touchdown, which is a visually complex navigation task in Manhattan with long and complex natural language instructions. So each of these tasks emphasize different language grounding phenomena. So in the complexity, these are in the complexity of the world observations, the language that's involved, the action space that the agent must reason over, the number of steps in the reasoning procedure, and how difficult the generalization process is during evaluation. And our goal with this benchmark, which we call SILK, is to provide a test bed so that the community can quickly test new methods that generalize to diverse grounding challenges and identify gaps in current tasks and setups for the creation of new environments. So here are some examples from Silk, from users playing these environments through the play utility. Because Silk is fully symbolic, we're able to render all of these in console. So on the left, we have someone playing NetHack, stepping through the environment. And on the right, we have a segmented Touchdown. So this illustrates our conversion process because some of these are visually rich environments, for example, with street view panoramas. So for Touchdown, we performed image segmentation on the street view panoramas to obtain a symbolic grid of object class IDs. And this basically turns a visually rich navigation task into a symbolic navigation task. So we do this for the different environments so that they share the same API. In addition to the SILK benchmark, we also provide a reference baseline model, which combines a number of recently proposed language grounding techniques. And for the first time, we're able to produce state-of-the-art numbers for most of these environments with a unified model architecture. We do see, however, that these numbers are far less than human performance. So this is comparing the green to the yellow, which is human. So there's significant room for improvement on this benchmark. And finally, we examine the question of whether training on symbolic variants of an environment is helpful for achieving visual end tasks, which is ultimately what we wanted. Alex, question?
Yeah, sorry. On the last slide, one thing I was curious about is why do you account, or like, what is it about the tasks or the model specifically that you think would lead to their differences in which is the best performance? So like in RTFM, SIR is far outperforming the previous state of the art, but in AlfWorld and New Scenes, the previous state of the art is far outperforming. Is there something about the task or the models that makes that happen?
Actually, for AlfWorld, and there's a caveat here that you see in the paper, these the previous state of the art rely on supervised learning. So they also have human trajectories that they're using, and we're not using that here. So that's a caveat. So these are about, I believe, the best you'll see with reinforcement learning. The light green here that we're showing. There's no particular reason to believe that a specific policy trained on one environment should generalize to another, because the action space of these environments are very different. The observation space is more or less different. So perhaps, I mean, I think that's an interesting question of whether you can make that work, but intuitively, we don't really think that should work. What we think should be possible is all of these environments have different modalities of input. For example, your visual observations, your language observations, some manual that parameterize the rules of your task. And the question is whether there are architectural decisions, for example, what kind of models you want to use to combine these different modalities of information, such that you perform well on the task. So we're looking for kind of architectural advances that generalize. Does that make sense?
Yep, that makes sense. Thank you.
Cool. So we examined the question of whether training on symbolic environments is useful for achieving visual end tasks, which is ultimately what we want because the real world is visual. So there's a prior work on this that's related here, which is Mohit Sridhar's work on the text adventure Elfworld. So Elfworld is a text variant of Alfred, which is a 3D kitchen environment where you're manipulating objects and trying to locate things and so forth. And what Elfworld is, it's the kitchen rendered in text as opposed to 3D. So they had a question of whether you can train on the text environment and then transfer the performance to the 3D environment. And they observed that indeed helped with training. We see similar results here with touchdown. So we find that training on symbolic touchdown is an effective way to do visual touchdown. So instead of doing reinforcement learning in visual touchdown, which is very difficult because you have to interpret continuous features, one can instead perform segmentation to obtain the symbolic touchdown and then do reinforcement learning in the symbolic variant. And when we do that, we see faster convergence and higher asymptotic performance given the same compute budget. And this suggests that symbolic environments may provide a good surrogate to visual end tasks despite having lower human performance upper bound due to loss of information from the conversion process. Any questions about this work? Or I guess these works, because there were a couple that I talked about here. Yes, Emmy?
Oh, hi. Sorry if I missed this, but I was just wondering about how you came to have the text for the manuals, because you mentioned, I think in your original work, that the games themselves were kind of procedurally generated, but does that mean the manual was also procedurally generated along with the game?
So these differ from environment to environment. So for RTFM, that's what it is. The manuals are also procedurally generated because we wanted sufficient coverage. Actually, one of the difficulties that I'll talk about last is finding manuals, because these are difficult to find in large quantities. So because and then we saw that if you didn't kind of show the model enough variation, it would just memorize the training distribution and wouldn't generalize. So for RTFM, definitely the manuals are procedurally generated. For Messenger, it's more difficult because the manuals are also written by humans. So then you don't have a lot of training manuals to learn from, but that's written by humans. For some of the other environments, there's no, quote unquote manual to speak of. For example, Elfworld, the manual itself is essentially an initial observation of what the kitchen looks like, and then for touchdown, it's the large instruction that you receive at the beginning.
Yeah.
And for NetHack, it's the goal instruction for the task that we like to achieve.
Yeah, thank you. Because I guess my observation was also the same as yours, that I don't know if it seems like many environments wouldn't come with a manual, especially at the sufficient granularity. So maybe I was thinking maybe the useful thing here would be to learn general representations of goals that transfer across environments, but I don't know how much that would actually work. So
yeah, that's a great point. So to sum up, I'm gonna speed up towards the conclusion here. So to summarize, we first covered generalization to new domains via reading domain text in the context of task-oriented dialogue. Next, for problems without domain text, we explored how to read the structure of the data in order to generalize in the context of semantic parsing. So specifically, we looked at reading database schema to parse queries on new databases, we also found that we can get even better performance by synthesizing adaptation data conditioned on the new database. And finally, for problems without supervised data from which to learn how to read, we showed some initial results on how to train reading policy learners that jointly represent observations and manuals. So I'm very excited about this thread of work on reading to generalize. I think what we've shown here are some exciting initial results, and there are many open follow-up questions that I like to investigate. So the first challenge, and this has to do with Emmy's point as well. The first challenge is how to find what to read. I think there are a lot of parallels here between what we're seeing in the work on prompt tuning. So in particular, what we want is we want a sufficiently diverse pool of text or manuals or instructions such that the models don't internalize any training domain. Because if you don't have that variety, the model tends to memorize the training distribution and it doesn't generalize. But we also want precise texts that are related to the problem at hand so that grounding the problem to the text is feasible. And when you have this kind of intersection, you find that for a lot of problems, it's difficult to actually do this by construction. So the question is, how do we find what to read? The second challenge is, once we have the data, how do we learn to read better? So for many problems, we simply cannot get tens of thousands of descriptions. And in those cases, it's difficult to train a reader. On the other hand, there's an abundance of web text and tutorial text, for example, online. So how can we use, for example, unsupervised or self-supervised learning to make training the reader more sample efficient? And the last point is subtly different from the previous one. And that is, once we have an idea of how to train the reader, how do we actually use it in practice? So recent work in few-shot learning with language models suggests that we need large language models in order to actually obtain few-shot behavior. However, these models are very slow for downstream tasks. For example, we can't use these methods in reinforcement learning and achieve any sort of reasonable frame rate. And without reasonable frame rate, we can't really learn any reasonable policies in the compute budget that we have. So as you can see, there are many opportunities on all fronts, from getting the data to implementing efficient learning and to actually deploying this idea to downstream tasks. I'm super excited about this direction. We have some current work in some of these areas that are happening right now, and I'm happy to talk to you about these ideas in more detail. All right, thank you. So these are my collaborators for the project that we talked about today. And I will take questions if you have any.
Great, thank you so much for that multi-part talk and so much interesting work. And we have some hands up for questions and clapping. So how about Nate first and then Emmy? Or okay, Nate.
Hi, I was just wondering about the lack of data sets, and I wanted to ask, has there been any kind of I guess exploration in applying this to interactive games, where instead of like reading a user manual or something, you'd just be reading feedback from the actual user?
Yeah, I think there's prior work. I can't name the paper off the top of my head, but I've seen prior work where people are doing policy learning, but instead of providing like supervised data to learn the policy or imitation learning, what they'll do is they'll provide language guidance on how to correct your behavior. And the goal is, can you reason about what you did before and what the correction instruction is in order to obtain better policy. So I've seen work like that.
Okay, cool.
Cool. I believe Shuyan has a question.
Thanks, Victor. It's very nice. So I have a question regarding the NetHack environment specifically, because I think for NetHack, they have a wiki about the one, right? Do you consider that as a manual to enhance the?
Not in this case. So this is actually one of the ongoing works we have, is how to use the NetHack manual, but not in this particular instance. So there's a larger open challenge at I believe we're actually called Meta AI Research and not Facebook AI Research. So there's
I apologize for that.
Oh, no, I didn't know that either. I just got the rebranding message recently. So there's a larger challenge on NetHack itself because the game is very difficult. Actually, you can try playing it, and maybe your advisors will get upset at me for saying this, but it's a very interesting game and it's very difficult. And the win rate that you see is, I believe for humans, it's something like 3%. So it's very difficult even for humans. So there's a reinforcement learning challenge on this task. It's convenient because it's super fast and because it's all in text, and it's very difficult. And there are lots of ideas on how to improve that. For example, one is by reading the wiki, because that's what humans do, because the game is so complicated and you want to reason about kind of levels and bosses and like good behavior. And some of those are specified in the wiki. But that's not included in the version that's in Silk or the version that's in the open source NetHack repository.
Right. I think even one difficulty is like which part of the wiki menu to locate it, or a very specific scenario or like a state.
Yeah.
How do we like align the state, symbolic state with the text?
Exactly. Yeah, and that's a great point. So actually there's some prior work on this. Brennevan at MIT many years ago started looking at this. And he was looking at it in the context of playing Civilization. So there's a paper on kind of doing Monte Carlo tree search. So you can do Monte Carlo tree search on Civilization, or you can do Monte Carlo tree search that's informed by the game manual. And he found that doing the latter was a much better idea. But then to actually make that work, he had to essentially manually curate how to do the grounding between the manual and the game state. I think an interesting question is, can you learn how to do that? And I think that's a pretty difficult task to actually do. But I think it's a very interesting research question.
Thanks. I think if I still have time to ask another question is like, what are your like recent ongoing works on this direction about reading manuals? Do you consider new environments or like mostly on new methods?
So we're looking at, for a lot of environments, they don't have the wiki, right? So it's difficult to, so ideally what we would like to see is you have a bunch of environments and then you have a bunch of natural language wikis. So it's kind of like RTFM, but it's actually natural language. And the hypothesis is if I look at a sufficient quantity of these environments and it's accompanying natural language wikis, maybe I can learn how to read and therefore generalize to new environments with new wikis. And these are all natural language. Unfortunately, I don't know of a good resource for doing that. And you can think about this in other contexts, like for example, in semantic parsing, if you had a bunch of comments on code pieces and you see sufficient quantity of well-documented pieces of code, can you generalize to new pieces of code? And that's difficult as well because we just don't have that. And a lot of these are just like noisy comments mined from GitHub, for example. So we're looking at this only within the scope of NetHack in terms of the wiki. We also have other things. So there's other resources available for NetHack. So one of the things I mentioned is like how to learn an efficient reader. So for a lot of these cases, we also have human playthroughs, or basically you have observations of how an expert behaves. So you observe some expert policy, but you don't really observe it in its entirety. So you can think about, for example, if you want to train a robotic arm, so we want to know how to actuate it in order to perform some task. But all we have is a footage of people doing it. So we don't have like, oh, in this precise moment with this state space, the actuation was this amount. So this is kind of known as third-party imitation learning. So the idea is you have some playthrough, or you have some expert trajectory, and you observe it in a kind of a partially observed setting. What can you draw from that? So for NetHack, we have actually millions and millions of human playthroughs, but we only have it in ASCII recording. So that's basically the similar case where you just like see a visual recording of people playing the game. So we can extract text from that. And the question is, can we use that to inform our policy so we learn better policy? That's another ongoing project. We also have people working on procedurally generating environments. So I think one thing that's exciting to me is, so if you want to do some task that's really complicated and you can't learn it from scratch from the beginning and you want to do some curriculum. Now, what people typically do is they handcraft a curriculum, and that's just not scalable for complicated things like NetHack. You can also do other things like using your agent performance to kind of sample environments to automatically derive a curriculum. But I think what's exciting is, can you read the wiki and use that to inform how you design curriculum? So can you reverse engineer from naturally occurring text on what scenarios are more plausible? So in doing that, you kind of shape the environment design distribution, and you use that to design realistic curriculum that the agent would actually see in real games. So that's another project that's going on. Some of these I'm not directly involved with, but it's kind of like what we're studying.
Awesome, quite impressive. Thank you.
Cool. Any other questions?
No, I don't see any more hands.
Cool.
So let's thank our speaker. I'll clap out loud. You can clap virtually. Thank you so much for joining us remotely.
Thank you for having me.
Yes, thank you so much. Okay, great. And I believe somebody is posting a link for students. Let's see if that's in the chat.
Yeah, I just posted.
Yes. Okay, great. Thank you so much. Okay, so students, go ahead and do that. Great, thank you.